everyone, and welcome to another episode of Chemistry with Capadia. This is going to be our last set of notes for Unit 3, where we're going to talk about the periodic law. So we've looked at the periodic table and we've kind of identified all of the cool parts about it, but where does it come from? How did we get from a bunch of elements to this lovely, fascinating table that is just organized in this amazingly brilliant way? So this is what we're going to talk about in this particular video. The notes for this are the second page of the periodic table notes that I gave you in class. So we only filled out all the way down to the radioactive elements. And then after that, it says a brief history of the periodic table. That is where we are picking up right now. Okay, so let's talk about a brief history of the periodic table, shall we? Oh, before we do that, just some background that we haven't really talked about yet. Protons, neutrons, and electrons are what do we call our subatomic particles. So these are what the atom is made out of. Every single element has a certain number of protons that is unchangeable. That's what defines that element, right? So that number is our atomic number, and it's the number that's on the top of the periodic table. It's a whole number. And that tells us the number of protons that that particular element has. If you take away those protons, or even one proton, it is no longer that element. So sodium has 11 protons, and if you take away one of sodium's protons, then it's not sodium anymore because it has 10 protons, so now it's neon, all right? So our protons alone determine the type of element. Next up, we have neutrons. Neutrons are neutral and have no charge, which is where this little zero comes into play up here. Oh, protons are positive, which is why it's a P+. I forgot to mention that. Neutrons are neutral, so they have a zero charge. The neutrons just add mass to the atom. They don't really have any other purpose than to give enough mass so that the atom is stable. All right, and we'll talk more about that in the next unit, but you cannot figure out the number of neutrons an atom has by looking at the periodic table. That is a no-go. And then the last step we have are electrons. So electrons are negatively charged particles, and so this is where this little negative sign comes into play. So let's put that on here. They are negatively charged, and they are the only way for something to become an ion is by gaining or losing electrons. So electrons have the ability to change properties of our elements. I can remove an electron from an element, and it'll still be that element. So if I remove an electron from sodium, it's still sodium, but now it's a sodium ion instead of a sodium atom, all right? In this, if we have a neutral atom, the number of protons is equal to the number of electrons. Number of protons equals number of electrons for any neutrally charged atom, and all we're looking at right now are going to be neutrally charged things. The reason that the electrons are important is because we also have something called valence electrons. So our valence shell is the outermost shell of electrons. So we'll learn later that electrons are kind of orbiting around the nucleus. And so the farthest ones away from the nucleus are going to be our valence electrons. And these are the only electrons that can be removed from an atom. And they're the only place that you can put extra electrons in an atom, or our valence shell, right? Everything in the same group has the same number of valence electrons, which we learned about when we were learning about the periodic table in the previous video. So everything in group 13 has 3 valence electrons. Our valence electrons are given by the last number in the group number. So group number 1 is 1 valence electron, group 17 is 7 valence electrons. So everything, all of those elements in that column are going to have the same number of valence electrons, but different number of total electrons. All right, so that's just a little bit of our background that we need. All right, so now let's just dive right in. So our elements, our periodic table. So the very, very first table was created in 1789 by a guy named Anton Lavoisier. He was a Frenchman. He created what was called the table of simple substances, which is this lovely table that is right here. And can I make it bigger? I can't make it bigger. But if you can kind of read what it says, you can notice that there are actually not, oh, here we go. Not everything on here is an element, right? So like some of these are copper, gold, iron, manganese, platinum. Oh, I guess platinum is an element. Zinc, these are all elements. This is probably a bad example column. Oh, here, look, this is not. Lime is not an element. Bartlett's, I don't even know how to say that word, not an element. Charcoal, not an element. A muriatic radical, who even knows what that is? Azote is not an element either. So not everything was an element. So we could not just keep this table. Then later on, when we had the ability to harness electricity, we were able to kind of like shock certain things and figure out what base elements make them up. And so our table grew a whole lot. So that in 1865, there's this guy named John Newlands, and he came up with the law of octaves. So octave comes from the word 8. So he said that every 8th element had the same properties or similar properties. He noticed a trend. But like at this point, he kind of sort of noticed a trend, and he was like, okay, this is kind of cool, but it didn't really work all of the time. So the greater scientific community was like, you know, we can't have 14 exceptions to one rule. Like it either works or it doesn't work. And they overall decided that it just did not work the way that he had it set up. And also, just like a little fun fact, because like scientists are super ornery, they didn't like that it was called the law of octaves because it sounded like music, and music and science are not the same. Like music is subjective and science is objective. So they were like, your name is terrible too. So they were really hard on John Newlands, and that's, you know, poor guy. He's okay though. I mean, he's dead, but he's okay. Okay, so before we get to the actual periodic table, let's talk about why it's called the periodic table. So the word periodic itself means that it occurs at regular intervals. So John Newlands was onto something with his whole 8th element thing, but it wasn't quite working. And he did not have the wherewithal to figure out how to fix it. He was just sad because, you know, nobody liked his idea. But along came this guy named Dmitry Mendeleev. So Mendeleev started thinking about what John Newlands did, and he was like, you know, if things occur at a regular interval, he's like, well, maybe we can organize them in the same way that we organize a deck of cards. So when we look at cards, cards are organized by the number going across, and then we have the suit. Oh, nope, sorry. They're arranged by number and by suit. So all of these numbers are increasing, and then all of our clubs are together, all of our diamonds are together, all of our hearts are together. So by suit, by number, and by property. So that's exactly what Mendeleev did. So he organized his periodic table with the mass of the element first, and then by the properties that they all had in common. And then what made him different from Newlands was this fundamental thing where he said that maybe we haven't discovered all of the elements yet, so we're going to leave room for the elements that we have not yet discovered. So his periodic table ended up looking like this. And so we can see that what he did is they're increasing in size going down, and then they're the same in properties going across. So it's kind of if we took the periodic table we have now and sort of shifted it. So he said that lithium, sodium, copper, silver, all of these things had stuff in common. Beryllium, magnesium had things in common. Boron, aluminum had things in common. All right, so this is how we came about. This is our very first periodic table. It was created. Well, it was actually created by Mendeleev's grad students because he was a professor, and so he was like, here, I have this idea, go make it work. I guess that's really the job of the grad students. And so from this, we found out that Mendeleev was kind of a genius when it came to these things because he was totally right. So let me draw your attention to this missing element right here. All right, so we don't have anything that's right there. So this is boron, aluminum, and then this should be the element that has properties similar to aluminum. So he called this Eka aluminum. And he predicted, based on the properties of the other elements that were around it, that the mass of this would be 68 grams. The density would be around 6 grams per centimeter cubed. It would have a really low melting point, and that it would be a soft metal. So he went one step further than Newlands did, and he said, not only do we not know what all the elements are, but I can predict what those properties are based on the gaps in my table. So this is why Mendeleev gets the credit and not his graduate students, because he's the one that did all the heavy lifting on this. All right, so the name of this element is actually called gallium, and it was discovered by a Frenchman years later, many years after Mendeleev made these predictions. All right, so the actual mass of gallium is 69.72 grams. Oops. The melting point, the density of gallium is 5.9 grams per centimeter cubed. The melting point is 29 degrees Celsius, which is a little bit higher than room temperature, so it's about 75 degrees Fahrenheit. And it's a soft metal. That was spot on. But if you look at all of these other properties, like this is really incredible. He did all of this with just the information he knew about the surrounding elements. So Mendeleev was really, really a genius. And so he is called the father of the modern periodic table for that reason. The father of the modern periodic table. This is not the color I wanted to write in. Still not the color I wanted to write in. My computer is not cooperating. There it is. Mendeleev gets purple because he's awesome. Father of the modern periodic table. Now, even though he did a great job, there is one fundamental problem with Mendeleev's table, and that's the same kind of thing that Newlands problem he ran into. When you organize the periodic table by mass, there are some things that just don't work. So let's take a look at what's going on here. All right, so if we look over here, tellurium and iodine, all right? Tellurium has a mass of 127.60 grams versus iodine is 126.9. So according to Mendeleev, iodine should be over in the other column. So iodine should be over here and tellurium should be over here. The problem is that fluorine, chlorine, bromine, and iodine all have a ton of stuff in common. So moving iodine, like iodine belongs with bromine or with fluorine, chlorine, and bromine. And we now know that it's one of the halogens, so like it's super duper important that it goes there. So instead of making the exception, there was another guy that came along and said, we can actually fix this problem without having to make any more exceptions. And this actually is not the only time in the periodic table this happens. Argon and potassium also have the same problem. Like potassium is very clearly not a noble gas, and argon is not an alkali metal. So this problem occurs a couple different times. So there's a guy named Moseley, and he fixed this problem by simply saying that instead of looking at the atomic mass, let's look at the atomic number. So the number of protons. Oops, this is the wrong way. Protons. So he said if we just organize everything by the number of protons, then it fixes all of our problems. We don't have to make any exceptions to any rules, and everybody is happy. So now the periodic table is organized by atomic number and not by atomic mass. So that is what our periodic law says. So our periodic law states that there is a periodic repetition of physical and chemical properties when you arrange the elements by increasing atomic number. So if we put them in order of atomic number and property, then we can look at a whole range of things. Physical properties are in common, chemical properties are in common. We got a lot of stuff going on. And so we've already talked about how like everything in all of the group, like everything in group 1 is an alkali metal. And in the next unit, we're going to talk about how there are things in the periods that we can talk about as well. All right, so periodic law, bada bing, bada boom, bada bang. All right, this has been another episode of Chemistry with Wikipedia. I hope you learned something, and until next time, keep on chemin'.